Hello and welcome everyone to the third lecture in MEC 3430 Automotive Engineering Fundamentals. On this lecture we're going to look at internal combustion engine configurations, dynamics, and valve train. So what did we look at in last class? Well, we looked at the basic internal combustion engine components and operation. We talked about why we're studying internal combustion engines. We talked about definition of what is and what isn't an internal combustion engine. We then spent quite a bit of time looking at the different components and terminology. We then briefly talked about spark ignition and compression ignition, which we're going to talk more about that in the next lecture after this. We then talked about four-stroke and talked about two-stroke very briefly, because two-stroke is not commonly used in automotive applications. Okay, so in this class, we're going to look at common internal combustion engine configurations. We're then going to look at internal combustion engine forces and dynamics. And then finally, we're going to end up with internal combustion engine valve train configurations. Okay, so there is a need for multiple cylinders. So when vehicles were originally coming out in the early 1900s, they were generally single cylinder engines, so just one cylinder. Well, if you think about a single cylinder, well, if we need more power, well, we have to increase the displacement, i.e. more fuel and air can be burned. Now, the problem with this is that you eventually hit a physical size limitation as to how big you can possibly make your displacement. And there's no real possibility of increasing the size, at least not in terms of from a manufacturability or from a being able to accelerate the mass up and down standpoint. So eventually engineers and automotive manufacturers said, well, there's got to be a better way than just keep making this cylinder larger and larger and larger. So eventually they figured, okay, well, why don't we design engines with multiple cylinders? So with multiple cylinders, we can have shorter stroke and a smaller cylinder. That means you can have a higher maximum RPM. A smaller cylinder equals more heat transfer, and this equals less knock chance or lack of ignition. Now, knock is related to spark ignition, lack of ignition, more so compression ignition. We'll talk about this later as well. Response goes up with more cylinders because you have more power strokes per cycle, and we'll look at this when we look at torque curves and how they differ with the number of cylinders in your engine. More cylinders means a longer or deeper engine crank. This means more torsional vibration, so this is a bad thing. If you have a longer engine or crankshaft, there's more possibility of vibrations. This is bad. Additionally, more cylinders means more mechanical losses. This is going to mean lower efficiency. So even though you have higher maximum RPM, you're going to have a lower overall efficiency. But generally, multiple cylinders, the higher maximum RPM overtakes the lower efficiency. Okay, so it's been decided we pretty much need multiple cylinders to be able to produce the power levels that we want in most vehicles. So how are we going to arrange these multiple cylinders in an engine or in an engine block? So there's three typical configurations that we're going to look at in this course. Now there are other configurations, but they're not very common in most automotive applications, so we're not going to focus on those. So the three that we're going to focus on in this course are inline cylinders, where as the name suggests, if we look at this first image here, all the cylinders are arranged in a vertical plane, so they move up and down in one straight line. V opposed cylinders, basically the cylinders are on either side of the crankshaft in a V shape. And then horizontal or flat, essentially if you took the V and squished it and flattened it horizontally. So yes, there are cylinders on either side of the crankshaft, but they're now moving in a horizontal plane as opposed to the V formation where it's kind of on an angle to the horizontal. So these are the three main configurations. Now, why might you choose one of these different considerations? So inline cylinders, well, there's less issues with balancing. They're mechanically simpler and less maintenance. The issue though is as you get to larger engines, it's awkward to fit as the number of cylinders increases. Generally, inline engines are limited to 6 cylinders. If you have a 4-cylinder engine, it's almost always an inline. A V4 is a four-cylinder V-opposed engine is very, very uncommon. Traditionally, inline cylinders, you'd have an I4, so inline 4. I6 is also common, but inline 8s or larger are very uncommon simply because of how large and awkward it is to fit them in most chassis or most automotive vehicle bodies. V-opposed cylinders, what are the pros and cons of those? Well, they're compact, easy to fit as the number of cylinders increases. So for V engines, you tend to see these come into play once you get around 6 cylinders, so V6. V8 is a very, very common performance engine. V10 and V12 are also seen on more performance-oriented vehicles. Issues with V-opposed, must take care to balance the engine, make sure we don't get unwanted vibrations, and it's mechanically more complex. Now for horizontal flat opposed cylinders, these things are inherently balanced. They have a low center of gravity and they're easier to cool. However, they are much larger. If you can imagine the V's, if you were to flatten the V out, that means it's going to take a much larger footprint in your vehicle. Maintenance is also very difficult. If you flatten out your engine, that means things as simple as trying to change, for say, a spark plug. Well, now your engine head is squishing into the side of your engine bay. So trying to get at anything on the engine is very, very difficult and annoying. So maintenance is quite difficult. Okay, so for the next few slides, we're going to look at some common engine configurations. We're going to look at how the cylinders are connected together on the crankshaft and how their phase is aligned. And then we're going to look at something called firing order. Whenever you have multiple cylinders, the design engineer has a choice as to which cylinder fires with regard to the other cylinder and how many degrees out of phase they are. So we're going to look at inline engine, then V engine, and then also flat as well. Now for these next few slides, essentially we're going to look at some common configurations. They're going to say how the connecting rod journals, how many degrees out of phase, the firing order, and how often do you get a power stroke. We're also going to look at a typical diagram that displays how the different cylinders, what strokes they're going through relative to each other. So if you look at this first inline twin cylinder, we have cylinder number 1. If we start at top dead center of cylinder number 1, we then have intake, compression, power, exhaust. While the first cylinder is doing intake, the second one is doing compression. While the first one's doing compression, the second one's doing power. First one doing power, second one doing exhaust. First one doing exhaust, second one doing power. So you should be comfortable with, if you're asked to reproduce one of these diagrams, you should be able, given the engine configuration and the number of cylinders of the name, you should be comfortable with creating or filling in the blanks on one of these charts. So I'm not going to go through all these charts in detail because they are essentially relaying the same information just for different configurations. So at this point, I'm just going to move through these slides so you can pause the video and look at these configurations as you see fit. So in this one, we have inline twin cylinder and inline side-by-side twin cylinder. On the next slide, we have an inline 3-cylinder and an inline 4-cylinder. And then finally, inline 5-cylinder and inline 6-cylinder. And finally, the very uncommon but still sometimes used to be used inline 8-cylinder. Okay, so now we're going to look at horizontal or flat engine configurations. So we have the flat twin cylinder or flat 4-cylinder. We have the flat 6-cylinder, which is actually more common in aviation engines. And then we have the V engine configurations. We have the V twin cylinder. We have the very, very common V6. Notice we don't even mention V4 because that's not a common engine configuration at all. We have the V8, which is a very common engine configuration, and there is actually a multitude of different firing orders that will give what is felt to be optimal balancing and power output. Notice different engines here will have different firing orders. This is a diagram of the distributor cap for muscle car or 1970 type engine, V8, and simply showing how the cylinders are fired on this distributor cap. So this distributor cap spins around, and as it hits its various points, it'll fire the different cylinders. Okay, so now that we've looked through the different common engine configurations, we looked at their typical firing orders and how the cylinders are arranged on the crankshaft. Well, how do we actually generate torque from the engine? So torque is indication of work done on the piston by the expanding combustion process. We knew that the internal combustion engine creates useful work by combusting some fuel, increasing the temperature and therefore the pressure. So we know torque is equal to force times the distance. So for the engine, the force is applied to the crankshaft connecting rod journals. And we must actually do an integration along the rotation, or an angular integration along the rotation of the crankshaft to get the average force or get the total torque. So if we get a simplified formula, well, torque is just equal to force times the distance, or force times r. So if we look at the maximum, when we have a right angle to our force vector, we have our, if we look at this diagram, our small little r, that's our moment arm that is at a 90 degrees to our force vector. Well, if we take force times r, that's going to give us our torque. So T is a torque generated, or F is the force applied to the crank, and r is the effective crank arm radius. So this is the torque that we might be generating during a power stroke, and actually this is only at one instance. As we said, we'd have to integrate throughout the entire rotation of the power stroke to get the average torque, or the torque being applied. Well, what happens when there isn't a power stroke? Well, that's why we need what's called a flywheel. So this is a large disc mounted to the end of the crankshaft, and this absorbs excess energy during the power stroke, and this energy is slowly returned during the rest of the engine cycle. So in other words, it's kind of a buffer to smooth out the power. So if you look at the torque coming out of an engine, see, this is at the top of this diagram, we have this torque coming out of the engine, then we have this huge spike in torque, which is the power stroke. Well, we see the flywheel speed actually kind of smooths out this large lumpy torque curve. And now there is some variations in the flywheel speed, but it's kept within a reasonable limit. And this can actually be improved depending on the flywheel design, and also using multiple cylinders, as we'll see in the next slide. So the importance of a flywheel is to smooth out the torque or power delivery, to make sure that we don't get this very jerky power delivery from the engine going through its cycles. Now if you look here, as I said, this is the torque, engine torque for a given number of cylinders. So if we look at, say, the very simplest example where we have a twin cylinder engine, well, there's still a huge gap where there is no torque being applied. So this, even with a flywheel, you're going to have a very large flywheel to balance out the somewhat large fluctuations in the torque. And as we see, as we add number of cylinders, we go to 3, 4, 5, 6, and 8. By the time we get to 8, the torque, the average torque, is actually fairly, is not as much different compared to the mean torque value. So when we started a 2-cylinder engine, the ratio of the maximum torque to the mean torque was 4, which means we're getting very large fluctuations. By the time we're at an 8-cylinder, well, the ratio of max torque to mean torque is only 1.1. This means we don't need as large of a flywheel to balance out the power as we get more and more cylinders in our engine, because we have cylinders that are firing more frequently. We have more overlap between the firing cylinders. So we can actually get a smoother operation come with more cylinders. Now, of course, this doesn't account for the inherent vibrations in the crankshaft because of the larger crankshaft. At least in terms of power delivery, generally responsiveness and smoothness increases with the number of cylinders. Okay, so for the next few slides, this is about balancing and making, how do we balance the forces from multiple cylinders. Now, I'm not going to comment too much on these. I'll let everyone read through these slides at their leisure, but I'm not going to spend too much time on these, and I think just reading through these bullet points is sufficient. So there's the first type of method, which is the harmonic balancer, which is a tuned rubber torsion / vibration damper. There's another type of harmonic balancer called the viscous fluid torsional vibration damper. And then finally, we have harmonic balancing via shafts. Now, this is a bit interesting in that we actually add additional shafts to the engine assembly, which have counter masses, or masses on the counter shaft to actually balance the engine rotation. So it's using more of a physical rotating mass to actually balance the forces from the multiple cylinders. And then finally, this is to balance the vibrations, but we still have to connect the engine to the vehicle chassis and or body in some way. And there are some engine configurations that no matter what you do, you can't eliminate all balancing issues. And most of the time it becomes it's not worth trying to figure out all the balancing issues. And a lot of these issues can actually be dealt with via flexible bushing mounts. So we attach the internal combustion engine transmission to the vehicle chassis with flexible elastic couplings, which isolate the vibrations from the internal combustion engine transmission from the chassis. Therefore, the passengers don't feel it as much. Now, these don't always work. My grandma had a 1994 Chevrolet vehicle that no matter what you did when you're at idle, the whole vehicle shook. That's likely because the rubber bushings had actually worn out and had become brittle, so they were no longer providing isolation. So these engine mounts can wear out over time. Okay, so we talked about the engine, how it actually creates torque, but we're going to look at some of the details and some of the forces that are occurring in the cylinder. So there's two types of forces we're going to look at: gas pressure and inertial forces. So the forces directly related to the gas pressure in the cylinder are called the gas pressure forces. So if we look at during compression stroke, in-cylinder pressure increases. So we're going through our compression stroke, we're increasing the in-cylinder pressure, while pressure always pushes outwards. In other words, the gas pressure during a compression stroke is going to oppose the motion of the piston. So the piston's trying to go up, trying to compress that air, fuel, or just air mixture. But the gas pressure that's building up in this cylinder is going to oppose the motion of the cylinder. And this increasing pressure is actually going to put tons of stress on the wrist pin connecting rod and crankshaft. Now, as combustion starts to occur, well, that means temperature goes up and pressure goes up. So the cylinder volume is going to expand due to the pressure exerted on the cross-section area of the piston, and that's actually going to be an assisting gas pressure. Because of this gas pressure, we're now in the power stroke. The piston wants to move downwards. Well, the pressure is increasing because of the combustion. It's going to push down on the piston, and therefore it's going to be an assisting gas pressure force. So during the compression stroke, gas pressure opposes the motion of the piston. During the power stroke, gas pressure assists the motion of the piston. And then we get the work coming out of this power stroke is just equal to pressure times area, or force times the distance, which is the stroke, and that's going to give us the work. So we can actually calculate the work done from the assisting gas pressure during the power stroke. So the main point here, gas pressure opposes during compression and assists during power stroke. Now, if we look at the other way, the other type of force, the inertial force, well, it's actually the opposite. So the inertial forces are due to mass of the piston, the wrist pin, and 1/3 of the connecting rod. So during compression and power stroke, these inertial forces create tensile stresses. And during the compression stroke, the inertial forces are assisting, whereas during the power stroke, the inertial forces are opposing. And these inertial forces are directly related to engine speed. As the engine spins faster, we're going to have stronger acceleration forces or higher acceleration or accelerations, and therefore higher inertial forces. So how do these two types of forces, the gas pressure force and the inertial forces, how do they interact? Well, basically the forces created by gas dynamics and inertia oppose each other. So gas force during compression cannot be changed. So the gas force when we're compressing the intake charge, well, that force cannot be changed. We can't change that we're taking some volume and trying to compress it. However, during the power stroke, if we include more fuel, we can actually change the gas force. As we add more fuel into the cylinder, assuming we can burn it all, we're going to get more gas force during the power stroke. So we can actually vary the amount of fuel going in to alter the amount of gas force during the power stroke. Now, so this means that if we're trying to get more power and overcome inertial forces, we can simply add more fuel up to a certain limit, assuming we can burn it all. So at general low engine speeds, the gas forces dominate. That's because, remember, inertial forces are proportional to engine speed. So low speed gas forces dominate. So you see in this diagram here, during the compression and the power stroke, the gas forces dominate. At higher engine speeds, inertial forces dominate. So if we look here during the compression stroke of a high-speed engine, we see the inertial force is going to dominate and create the resultant force going upwards, and same thing with the power stroke. Now you might ask, well, how the heck do we get a power out if the resultant force is upwards? Well, the thing is to remember is that an inertial force is not actually a physical force. It is a fictitious force that occurs when you have a rotating frame of reference. So the net force acting on the piston is still down during the power stroke. This is an easier way to conceptualize what's happening between the rotating mass and the gas dynamics. So this also implies that when you are trying to go compress your intake charge, it's actually easier at higher RPM because we have the inertial force assisting as well. So the main thing to take away from here, we have gas force and inertial forces. Low engine speed, gas dominates. High engine speed, inertial dominates. And gas and inertial forces oppose each other. Okay, so there's another consideration within cylinder forces as well, is that due to the line of action between the connecting rod and crankshaft, forces are in multiple planes, i.e. forces aren't just up and down. We'll have forces acting at angles, which means we have a side thrust force with this Fs. Now, unless you're a top dead center or bottom dead center, there will always be side forces because of the line of action of the force going through the connecting rod. You're always going to have these side thrust forces. Now, these side thrust forces are generally unwanted. So what we can do is we can offset the wrist pin, and it can help reduce these side forces. This can reduce piston slap, in other words, the piston bouncing back and forth in the cylinder wall, and also reduce friction. Remember, friction is proportional to the normal force. If we have a strong side force, that means there's going to be a strong friction between the piston and the cylinder wall, and that's going to cause inefficiencies. So we want to reduce the amount of friction that's occurring. So we can use this offset wrist pin concept to reduce the amount of side thrust force. In general, when you install a piston in a cylinder, there's an arrow on the crown to mark the front of the engine to make sure that you install it correctly, such that the wrist pin offset is in the correct direction. Okay, so I talked about internal combustion engine configurations, talked about their force dynamics. I'm now going to talk about timing mechanisms and valve train. So these are timing drives, so how do we control when the valves open? So chain drives are generally used when there is a large delta T. In other words, there's a large time difference. So to compensate for stretch, automatic chain tensioners are used. We can also have belt drive arrangements which use jockey or idler pulleys to obtain tension. Then finally, we have gear drives, which are used when high forces are expected. So medium to heavy duty diesel engines and reliability is essential. So most vehicles are going to use a belt drive. Why? Because belt drives are much cheaper to implement than the other two. Chain drives are used on some vehicles where there may be more conscious about longevity. However, if the chain drive ever does go bad, it is a very large and painful job to be able to change it out. Changing a belt, fairly simple. Changing a chain drive is not as simple. Gear drives are very seldomly used in most automotive applications. Again, they might be used in very heavy-duty diesel, i.e. transport truck, but not really the automotive sector. And here's just some configurations of timing chain and belt drives. Depending on whether you have single or multiple overhead cams, you can have different configurations. And we're going to talk about what overhead cam and single and double twin overhead cam, what that means in the next slide. So I'll let you go through these diagrams on your own as you like. And here's some diagrams of geared timing drives. Again, very uncommon unless you're dealing with heavy duty diesel, typically not in automotive. Okay, so let's look at the concept of valve timing diagrams. So when we discussed the 4-stroke engine, we said each stroke has a unique function. Well, it's not quite true because when you have your valves opening and closing to either let intake in or exhaust out, we have something called valve overlap. In other words, the intake valve doesn't open when the intake stroke starts. The intake valve, IO, intake valve open, actually starts during the exhaust stroke. So you have something called valve overlap. You have a period where the intake valve is open and the exhaust valve is still open as well. And this is because you can't get necessarily everything out just during the exhaust stroke. You want to have some overlap to allow for more of the exhaust to escape. So we generally have this valve overlap. Now, if you look at the intake valve in most typical engines, so IO is intake valve open, we see intake valve close. That doesn't happen until you're quite a ways into the compression stroke. So in our diagram where we said intake stroke stops at the bottom when you're at bottom dead center, well, that's not actually true. It actually continues a good way into the compression stroke. So once we're in the compression stroke, eventually that intake valve closes. We then have our compression period. We have our power stroke. And actually the exhaust valve opens partially way through our power stroke. So the cylinder hasn't even gotten all the way to the bottom, or piston hasn't gotten all the way to the bottom, and then we're opening our exhaust valve. And then the exhaust valve actually stays open for quite a long duration and into the intake stroke. So to say that a 4-stroke engine is an engine that has 4 distinct phases where each stroke is completely isolated, well, that's not really true. There's overlap between the exhaust and the intake and compression. These are 2 possible valve overlap strategies. As we say, more valve overlap gives you more engine performance. Lower valve overlap gives you better exhaust performance. And now the only thing I want you to take away from these 2 slides, though, is that the strokes are not completely isolated individual processes. There are overlap between the strokes because of when the valves open and close. And to take away the concept that generally there is always some type of overlap between intake open and exhaust close, and exhaust open and intake close. Okay, let's look at some common valve train configurations. There's only 2 that we're going to look at in this course. So the first is the overhead valve. So this is where the camshaft is in the engine block, and we use various components, predominantly a push rod, to actually actuate the valves. So the crankshaft camshaft, is actually in the engine. For the overhead cam, as the name kind of implies, the camshaft is actually in the cylinder head as opposed to in the cylinder block. In general, overhead cam can be made with less components, which means less mass, which means more efficient. You can also have separate camshafts for intake and exhaust, so you can have different profiles for your intake and exhaust, which is good. So single overhead cam, which means one cam does intake and exhaust, gives you better low-end torque. But double overhead cam gives you better high-end horsepower because you have less mass that's rotating on each camshaft, so you can rev higher. I should also mention for overhead valve, one of the main advantage, or the main advantage, is that it's a more compact design, which allows for more shallow engines and therefore potentially lower center of gravity. The Chevrolet Corvette, up until the latest iteration, I actually have to check the C8 Corvette, but up until the C7 Corvette, which was up until 2019, if I'm not mistaken, they all had overhead valve engines so that we could have a lower center of gravity in the Corvette. Now, most super performance cars use overhead cam because they want to have more high-end, high-revving horsepower. But for most American supercars or sports cars, we're actually more concerned with low-end torque and more of a compact, low center of gravity. So that's why most go with an overhead valve in that context. Okay, so as we have this camshaft, it's basically a shaft where we have these rotating lobes, or different lobe profiles, which allow either some type of connected mechanical device to move up and down so we can actuate the valve. So we look here at this lobe profile here, we can actually see that as this camshaft spins, we have different profiles for the valve lift, for the velocity of the actual valve, and then the acceleration of the valve. So the main point to take from this slide, and the only point I really want you to take, is that when a camshaft or when an intake or an exhaust valve opens, they don't just magically spring open to full open instantaneously. There's actually a curve that they follow in terms of their open and close. So when we label those valve diagrams, intake open or exhaust open, or intake close, exhaust close, remember that there's actually a lag between when that actually fully occurs. That's part of the reason for the valve overlap, is that it takes time for the valve to fully open and to fully close. So that's the only thing I want you to take away from this slide. Okay, now here's a diagram looking at for an overhead valve configuration, all the different components. We have our camshaft, which is in contact with a cam follower, which then connects to a push rod. So another name for an overhead valve engine is a push rod engine. Particularly push rod V8s are quite common. This then connects to a rocker arm, which is connected to a rocker shaft. We then have the return spring, which basically keeps tension on the valve to hold it closed normally. We have our retainer and then a keeper as well. So those are the main, and then the actual G, the poppet valve itself. Now these are some configurations for overhead camshaft and valve operation. I'll let you look through these. These are all overhead cam configurations. And then some more overhead cam configurations as well, looking at two of them where they have dual overhead cams. There's some considerations when you're actually designing the valve. We want to expect life expectancy and efficiency, so we want to select appropriate material for the valve and valve seat. It's a high temperature, there's dynamic stresses, there's corrosion, you want to consider wear resistance. We also want to consider the shape of the valve seat to limit flow restrictions through the curtain area. Now the curtain area is basically the flow area between the valve seat and the actual valve itself. So the only thing I want you to take away from this is that valve design is actually quite complicated, and that it's actually quite a difficult piece of the engine to design because of all the criteria that's placed on it. Okay, so as I said, ticket out the door, we're going to have those discussion boards set up for ticket out the door. Again, that's something you learned today, and something that where the explanation was not clear or something that was confusing. All right, thank you very much for your attention, and I'll see you next lecture. Bye.